All right, welcome back to topic 2B. Real fast, let's go back to our question that we kind of left off a little bit about we calculated W, but we didn't calculate Q and U. All right, so for U, all right, so for U, a perfect gas, we're going to assume that U is only proportional to the temperature. Only proportional to the temperature, right? Going back to this one was it? Right. That's basically going to be equal to 1/2 kT, right? The sum of all the different possible movements, right? And nothing to do with the pressure or the temperature or any of that particular stuff, right? Or the volume, I should say, right? And so for all of these, whether it's reversible, constant internal pressure, or freely, if it's a perfect gas, we would assume that U, delta U, is going to be 0 for all of them, right? And so if delta U equals 0, then that means that for all of them, Q is going to be opposite of W. Right? Q is going to be opposite of W. Same value, but opposite sign. Right? So that's how we would get Q heat for each one of the 3 different things. I think if we had like for reversely was negative 6,000, and then was negative 3,000 joules, and then 0 for freely, well, the work would be same value, just opposite sign. Now let's move on to section B about enthalpy. All right. Now the technical definition of enthalpy, H, is the sum of internal energy and work. Right? Work being P times V. Right. Now functionally though, our change in enthalpy here is going to be equal to the heat, right? The heat at constant pressure. That's the main point, is that it's at constant pressure, right? And if a system results in very little volume change, basically if PV is very close to 0, right? Let's say something only involving solids and liquids, where the volume change we would expect to be very, very small, then enthalpy is approximately the same as internal energy, right? But if there is a significant change in volume, let's say changes in the amount of gas, right? Because gases go from, we go from the volume changes 100-fold, right? Then our delta H would be the internal energy plus P times V, right? And this is what how do we get this? That's PV equals nRT, right? If we change the moles of gas, this is the change in the P delta V, basically, right? Delta N, the moles of gas, times R times T. Right? If there's a significant change in the volume, aka number of moles of gas is changing, right? Now, just like our internal energy, enthalpy is going to increase as our temperature increases, right? Because think about this, right? If enthalpy is internal energy, we already, plus extra stuff, we already said that internal energy increases as the temperature increases, right? So if U goes up, then H by definition also has to go up, right? So the quotient of this change, the change of enthalpy as the heat changes, this is the heat capacity at constant pressure. Remember, heat capacity, constant volume was squiggly U over squiggly T at constant volume, right? This is the same thing where we have enthalpy over temperature at constant pressure, heat capacity, constant pressure. Right? Just like we said before with the molar heat capacity at constant volume, we have the heat capacity constant volume. We can have molar heat capacities, we can have specific heat capacities, right? Same difference, nothing changed there. All right, we can rearrange our relationship between the enthalpy and the temperature, just like we did with the constant volume heat capacity, to get like delta H equals heat capacity times delta T, right? And delta H at constant pressure is by definition also Q, right? By definition also Q. All right, this of course assumes that the heat capacity is constant over the range of temperatures, or as it says, is close enough for approximation. Right? If our CP changes too much, though, then we use some sort of a more detailed breakdown. Right? Going back to topic 1, I talked about the virial equation of state, where we kind of break it up into smaller and smaller pieces. This is the same basic idea, right? Our, in this case, go back, molar heat capacity at constant pressure is constant A plus constant B times T plus so on and so forth, right? Where A, B, and C are empirical parameters, right? Defined or not defined, but discovered for an individual substance. All right. If we wanted to relate heat capacity at constant pressure, heat capacity at constant volume, right? In general chemistry, we made no distinction between these two. We just said like C sub S or something like that. We just kind of kept it really, really simple. All right, but because energy can be expressed both as heat and work at constant pressure, but only in heat at constant volume, right, then the temperature of a constant volume system would be expected to change faster. Does that make sense? So for a constant volume, right, if constant volume, then we have no work, right, and only heat, right? And so all of our energy change is going to be expressed as heat, which means we would expect to see greater changes in temperature, right? At constant pressure, right, we can have work or heat. And so some of the energy will be expressed as work and some of it will be expressed as heat, right? Of course, it depends on the reaction. Not every reaction is going to have work, but in what we'll be looking at, most of them do. So again, we would expect our CP, our heat capacity, to be higher at constant pressure than at constant volume. All right. Think of it as like we're holding the line better at constant pressure than at constant volume, right? Because this should be changing a lot more. All right, and for a perfect gas, right, our CP minus our CV should equal N times R. All right, CP minus CV should equal N times R. Right, if you wanted to go through and do this, you would substitute in, this would be delta H over delta T, right? This would be delta U over delta T. And then basically like this is using the, like substituting things in for the ideal gas law, kind of putting it all in there. Not going to get that specific in it. We're mostly going to use something like this. All right, so if we want to look at a perfect gas, you see, make sure I'm not missing anything. Yeah, not missing anything. Let's say we found a perfect gas. It's found to be equal. There it is. I knew it was missing something. When 228 joules of energy is applied as heat, right, at constant pressure to 3 moles of argon, right, the temperature of the sample increased by 2.55 Kelvin. Calculate the molar heat capacity at constant pressure and the molar heat capacity at constant volume. Okay, so we We have a Q of 228 joules, right? We have an N of 3 moles, and then we have a delta T of 2.55. Okay, so if we were to do this, right, delta H is equal to Cp times delta T, right? We saw that result a long time ago, right? Cp times delta T. Okay, so, and our delta H is also the same thing as heat at constant pressure, right? Delta H is heat at constant pressure. So we would say that our 228 joules, which is the enthalpy and the heat at constant pressure, is equal to Cp times 2.55. Right, if we do that, then our Cp is going to be 228 divided by 2.55 is going to be 89.4 joules per Kelvin. Right, 89.4 joules per Kelvin. And then if you want to do this on a per mole basis, right, because we want molar heat capacity, then we're going to divide this by our 3 moles. Right, which would make the molar heat capacity 29.8 joules per mole Kelvin, right? So we're looking at 29.8 joules per mole Kelvin. All right, that one's pretty easy. Now to calculate the constant volume heat capacity, we're going to assume that this is going to be a perfect gas. That's the only way we can relate constant pressure and constant volume, is that it's going to be a perfect gas. Like we're gonna keep that, make that assumption, right? So our constant pressure minus our constant volume is N times R. Well, if we know our constant pressure is 29.8, right? N is 3, R is still 8.314. Right, well, our constant volume is going to be 29.8. That's right, let's do 3 times 8.314. Right, and then minus 29.8 gets me negative 13, and then times negative 1, I get a value of 13.2 joules, in this case, per mole Kelvin. Oh, sorry, joules. Okay, well, let me back up a little bit. We gotta make sure to do this correct. All right, let me back up. All right, this CP needs to be the base value, 89.4. Right, and 3, 8.314. Okay, let's try that again. So 3 times 8.314. All right, minus 89.4, right, times negative 1 gets me a CV of 64.5 joules per Kelvin. All right, divide that by our 3 moles, and that will get us our molar heat capacity constant volume, which is going to be 2.15, right, joules per mole Kelvin. Okay, 2 different answers, fairly easy to get, really. Now, moving on from there, we have a much more difficult example. All right, this is Cp for perfect gas. It's found to be equal to 20.17 plus 0.36665 T. So this is how we plotted this basically and seeing how CP changes over time related to temperature. I'm going to calculate Q, W, U, and H when the temperatures range from 25 degrees Celsius to 100 degrees Celsius at constant pressure. At constant pressure. So let's start off. Now we have CP, and we know that delta H is equal to CP times delta T, right? All right, and our CP is 20.17 plus 0.3665 T, basically, right? And we're going to take that, right, we're going to see what the changes are there. Delta T, we have to break it down. Goes from, the initial temperature to the final temperature. And the initial temperature to the final temperature. Right, if we do that, then we integrated that, right? 20.17 gains a T, right? And then this integrates up to 1/2 times 0.3665 T squared, right? And we would add the numbers up basically going from 25 degrees Celsius, which is 298, to 100 degrees Celsius, which is 373.15, each one of them. So this is 298.15 and 373.15, right? And this, on the left-hand side, this delta H is going to be the value of H at the final temperature minus the value of H at the initial temperature, right? But basically, it's still going to be delta H, right? We haven't done any integration there exactly. We just we want to break it down and make it look like everything else. That's how it works out. All right, now if we do this, all right, what would this be? This would be, okay, let's do 20.17 times upper limit 373.15 plus 1/2 times 0.3665 times 373.15 squared, right? And then minus 20.17 times 298.15, and then minus 1/2 0.3655 times 298.15 squared, right? We'll fit that in at the end, right? 298.15 squared. All right. Lots of math. But when we get our calculators, it'll make it a lot easier. All right, so big old parentheses, 20.17 times 373.15 plus 0.5 times 0.3665 times 373.15 squared. Parentheses, doesn't really matter. Minus 20.17 times 298.15 minus 0.5 times 0.3665 times 298.15 squared. That would give me an answer of, right, delta H of 4.33 times 10 to the 4th joules, right? Or 4.33 kilojoules, which is a really good number. Usually delta H's are in the kilojoule range, all right? Now, we found delta H here. Had to do a little bit of math here to figure it out, but we found delta H, right? And since this is constant pressure, we know that delta H is the same thing as heat, right? So our heat is also 4.33 times 10 to the fourth, right? We know heat is also 4.33 times 10 to the fourth. Ouch. Okay. Now, when we are trying to find, like that's H is done, Q is done, right? We know to find U, we're going to need to calculate, well, actually, there's two ways we can do U, isn't there? Well, no, there's only one way.